Hi everyone. So today we're going to continue on a system of linear equation. So last time we were talking about intersection between lines, and as we talk about, it's very straightforward. Two lines are either parallel. If you have two distinct lines, if they are parallel, they not intercept at all. If they are distinct but not parallel, then they must intercept at one point. And that's what's happening with lines in R2, linear equation in R2. But now what happens when you have intersection between planes? Well, intersection between planes, a little bit more complicated. So how does this work? So give you an example. So remember a system of linear, a system of linear equations in R3 will represent intersections between planes. So let's try to figure out what happened first. So in R3, two planes must intercept each other if they are not parallel. Okay? Parallel plane, they can be intersecting if they are the same plane, or they don't intercept at all. Okay? In R3, two distinct planes that are parallel will not intercept. Now, that actually mirrors what happened in R2 with lines. In R2, two lines must intercept if they are not parallel. Okay, and in R2, two distinct lines that are parallel will not intercept. Those are the exact same thing. Now, once again, that shows some similarity between lines and plane, but just in different dimension. And that's basically what linear algebra is about. It's about this geometrical object called lines or plane, but they're all represented by linear equation. That's the connection. And they all behave the same way, but just behave the same way, but in different dimension. That's the key. Now, here's also very interesting. If you realize this similarity, then hopefully you can understand what's happening and it makes sense to you. We call in R2, okay, R2, so that would be like the xy plane. And think about it, that means what we refer to as a two-dimensional space, because that's just like the paper that you have on your desk. Okay, in R2, two lines that intercept must intercept at a single point. They cannot intercept in any other object. Now, here the interesting parallel. So if you want to write it down, you should. In R2, two lines, which are one-dimensional, must intercept at one point. A point is considered to be zero dimension because you can't move anywhere. Notice the number that I just said, R2, 2. Lines, dimension 1. Intercept at a point, dimension 0. Dimension 2, dimension 1, dimension 0. Now, let's see if you can complete this statement. In R3, two planes that intercept must intersect in what? What should the object of the intersection be? And if you simply look at the Chromebook that's in front of you, if you're using a Chromebook, but if not, you definitely hopefully sitting inside a room, you can just simply look at the ceiling and the wall behind you. Then you should be able to identify what is the intersection between two planes going to be. As a matter of fact, in R3, two planes that intersect must intersect in a line. Intersection between any two planes must be a line. It cannot be anything else. And here, once again, is the pattern that you hopefully notice. In R3, 3-dimension, planes, 2-dimension, two planes, they're both dimension 2, must intercept in a line, dimension 1. So, if you notice that pattern, interesting thing about it is that that pattern continue on into higher dimensions that we don't know how to visualize. I mean, I can say the exact same thing when in R4, 2, we don't know what this object is called, but let's say this object is similar to a plane, but in 4th dimension, R4, and this thing would be 3-dimensional, and then their intersection would be 2-dimensional. So that's very interesting thing that's happening. But that is the basic idea of what linear algebra is about. It's about studying linear equations that represent different objects in different dimensions, but yet it behaves the same exact way. Now, so this basically tells me that the intersection between two planes is a line. So now what I'm also more interested in is this question. What is the intersections between 3 planes? So when you talk about intersection between 3 planes, there are quite a few cases to consider. So number 1, case 1. The 3 planes do not intercept at the same time. Therefore, there is no solution. When you have a system that has no solution, we have a name for that. A system is called inconsistent system if it has no solutions. Inconsistent. And that will be when your system have no solution. Now, why would these 3 planes have no solution? What causes this? Well, I'll show you a picture to illustrate that, but I do want to list all the cases first, so that way we can then look at the picture of all of them. And no, I'm not drawing you a picture because that's not very easy to do, but I did find a Google picture that I can show you. So what happened to case 2? Case 2 is the following. Case 2 is that the 3 planes, they do intersect, and they intersect at a line. So the system has an infinite solution. So this one have no solution. That's the first case. Case 2, we have an infinite solution. Case 3. The 3 planes intersect at one point. So the system has a unique solution. Has one unique solution. Interesting thing to note is the following. These basically tell me that when you talk about intersection between three planes, you either have one solution, infinite solution, or no solution. You cannot possibly have 2 solution, 3 solution, 10 solution, 12 solution, 2020 solution. No, it has to be either 1 or infinite. Otherwise, you have none. That's how it works. A system is called consistent if it has a solution, if you have any solution. Okay, if a solution set is not empty, that means it has solution. Whether it's 1 or infinite, it doesn't matter. It's called a consistent system. While if a solution set is empty, that means it has no solution, then it's called inconsistent system. Now, the question then will be, how does it work? Why the 3 cases? So the simple answer is the following. So before I show you the picture, let's try to kind of make you understand what's going on. Okay? So, whenever you try to talk about intersection between 3 planes, the general idea to understand how that works is to think of the following. Instead of looking for the intersection between 3 planes, how about we look at the intersection between only 2 of the 3 planes first? And then take the intersection between that, and then try to figure out what that intersection would do with the 3rd plane. So, think about it. We already established that intersection between 2 planes, if they are parallel, then they will have no intersection, and therefore it will be case 1, no solution, because 2 of the 3 planes are already not intercepting, then obviously the 3 planes cannot all intercept at the same time. Okay, assuming that the 2 planes that you choose of these 3 planes, they are not parallel, then they must intercept. And we already established when you intercept 2 planes, you get a line. So if you now want to find out what happened to the intersection between 3 planes, you are essentially looking for the intersection line between 2 of those 3 planes with the 3rd plane. Now what could happen? Well, that could happen one of 3 ways. The intersection line between the first 2 planes is parallel. It exists on a parallel plane as the 3rd plane. Therefore, does not intercept. That's case 1. 2. The intersection between the first 2 planes is a line, but that line is actually on the 3rd plane. Therefore, you have infinite solution because the line intercepts completely with the plane because it's on the plane. 3rd case, the line that is the intersection between the first 2 planes go through the 3rd plane. Just like you take up the piece of paper that you have and take your pencil and poke a hole through it. That's how it works. It goes through it. If that's the case, then it will only go through the plane at one single point. Therefore, one unique solution. Now, show you how this works. I did find a picture. I'm just trying to see if I can actually paste it. Oh yeah, I can. There you go. So show you this picture right here. So notice this picture have 5 images here. So let's see if I can actually write on this. So let's say this is A. Let's say this is B. This is C. Let's say this is D. And let's say this is E. So now I'm going to ask you to do the following. Before I reveal it, take a minute to think. Okay, you can pause the video if you want. A, B, C, D, and E. Which case is each of these pictures? So take a minute to think, and then I'll reveal the answer in a little bit. Okay, so pause the video, and then think about it. All right, so hopefully you have some time to think about it. So now let's look at each one of these. So let's start with the easy one first. So clearly, C here would be the one that have no solutions. Because in this case, you basically have 3 planes that are parallel to each other. And if that's the case, they're not going to intercept. And it should be pretty clear to you that B is also no solution, because in this scenario right here, notice that the purple plane and the blue plane are parallel to each other, even though the green plane go right through it. Okay, and so that one definitely have no solution. The interesting thing about it is that this last one right here, this one also have no solution. Okay, the reason why this one no solution is the following. Imagine you look at the intersection between the red and the green plane. It will form this one line right here. Let's see if I can just highlight it. This one line right here. Oops. This one line. But that line, oh, actually, well, you can't see it. All right, let me use a different color. Maybe blue. Or maybe highlight. Let's see if I can highlight this. So this one line right here. So this line is actually parallel to the blue plane. So therefore, it's not going to intercept it. And if you look at the intersection between the green and the blue plane, is also form a line that's not going to intercept the red. Okay, just like the intersection between the red and the blue plane is also parallel to the green plane, so therefore it's not going to intercept it. So essentially what you actually form inside here is a triangular prism. Okay, and therefore you have no intersection. A, on the other hand, would be the case where there are infinite solution. The reason why this will have an infinite solution, because it's showing that if you look at the intersection between these three planes, they all intercept at the same line. Okay? And that's the idea here. But you can also think of it as that the intersection between the green and the blue plane is the line that's on the red plane, and therefore provide infinite solution. And for the last one, you can guess, because there's only one choice left, this one have one unique solution. So where is the unique solution? It's right here in this point, where the intersection between the three planes are going to be. And as a matter of fact, if you think about this one, you can also imagine that the green and the blue intersect along this line that go horizontal. And then the red and the green intercept this line that go vertical. And then the red and the blue intercept this line that go front and back. And these three lines intercept in this one single point, and therefore become one unique solution. All right. If you're still unclear about that, we can definitely talk more about it during class. Now, I only have one last thing I want to show you. And then that will be it. And then if we have time toward the end, maybe we'll do a system of equation together with three variables. But once again, as I say, I do want to introduce what we call the matrix method to solve the system of equation instead. So next thing I want to talk to you about is this term. It's called homogeneous system. A homogeneous system is basically when you have a system where all the equations are equal to 0. And that's referred to as a homogeneous system. But of course, for us, we are all more focused on what we call a linear homogeneous system. So a homogeneous system of linear equation is a system in which all the equations and I do mean all. It have to be all. It cannot be just some of them. All the equations are equal to, oops, try to write equation, equal to 0. Therefore, example will be the following. A system of three equations with three variables that is homogeneous will look something like this. Now, what is the significance about a homogeneous system? Well, there's something very important about homogeneous system. Not just that we have a lot of application that we eventually will see, but also from a geometrical standpoint is also quite interesting. First of all, you need to understand is what happens when you have a linear equation that go through that equal to 0. Okay? A linear equation, regardless what dimension it's in. So if you can think of a linear equation as in R2, which is a line, or R3, which is a plane, a linear equation that is equal to 0 must pass through the origin. And if you think about it, it makes sense. The reason why it must go through origin, meaning that the origin must satisfy the equation. Which, if you think about it, if you plug in 0 for x, 0 for y, 0 for z, regardless of what these coefficients are, you will get 0 as an answer. Now, why is that important? Because if you think about it, I'm looking for the intersection between these three planes. And these three planes all equal to 0. And I just told you, a linear equation that's equal to 0 must go through origin. And so if you think about it, hopefully you come to this conclusion. And that would be this: a homogeneous system is always consistent. It always have a solution. Why? Because I just told you, all the equation, if all the linear equation, if they equal to 0, they must go through origin. That means this first equation go through origin, the second equation go through origin, this third equation go through origin. That sounds like origin is the one place where all three equations that go through and therefore become an intersection. So therefore, a homogeneous system must have the 0 vector as one of its solution. Now, yes, I did say one of its solution because a homogeneous system can not just have one unique solution, which is what we talk about right here, case 3, but because it's consistent, it could also have infinite solution. And if that's the case, that means that our 0 vector must be one of the many solutions involved. So as a matter of fact, a homogeneous system must either have one unique solution. Remember, it has to be consistent, therefore it must at least have one solution. But if it does have one unique solution, that solution must be the 0 vector. It cannot be anything else. Or infinite solution. And in its infinite solution must include the 0 vector in its infinite solution. So very important, one of the most important thing about homogeneous system is that it's always consistent. It always have a solution. The things that we want to know about homogeneous system is not whether it's consistent or not, because we know it's always consistent. The one thing that we want to know about homogeneous system is whether it has one solution, which is the 0 vector, or have infinite solution. And of course, somehow that would tie into what we need to do. Now, maybe we can try to solve a system together just to show you the old way to do it. Since I have about 6 minutes before, like 30-minute mark, we only have 24 minutes. So show you how to solve a very simple system. So maybe we just do the system that I mentioned to you before. Example, let's try to solve this system right here, which I believe is is x plus 4y plus 3z equal to 1. And then 2x plus 5y plus 4z equal to 4. Negative x plus 3y plus 2z equal to negative 5. So right now, looking at this system, I really don't know what the solution is. So what I'm going to try to do is try to manipulate the system in such a way that will allow me to see what the solution is. Okay, so how do we do that? So the method that we are going to be using is actually has a name. Some teacher would probably, you might remember learning it as called the addition method, because it requires you can add equations together to cancel out a variable. But for us in linear algebra, we actually call that the elimination method. The idea of elimination method basically meaning that you eliminate variables in your system. And the general idea is that right now we have 3 variables, 3 equations. What we're going to try to do is eliminate one of the variable, and by doing so, would eliminate one of the equation. So therefore, the system becomes smaller, 2 equations, 2 variables. And then we do that again, that will result in 1 equation, 1 variable, which allow us to solve for that equation. So how do we do that? So the easiest way to do that is to take the first equation and take the last equation and add them. So that cancel out. That becomes 7y plus 5z equal to negative 4. Notice this equation has only 2 variables in it, which is good. Now next thing I'm going to do is I'm going to take the second equation. I cannot use the same 2 equation again because it will generate the same exact result. So I'm going to take the second equation. I can neither do the first or the last equation, but here notice the last equation does have a negative. And so if I multiply by 2, I will have negative 2x plus 6y plus 4z equal to negative 10. And so now what I'm going to do is I'm going to add this together. And so these 2 cancel out. I have 11y plus 8z equal to negative 6. And now notice that now I have 2 equations with only 2 variables left. That's what the elimination method is designed to do. Okay, so now what I'm going to do is, that's an 8, is try to combine these 2 equations together. So the easiest way to do that would be to multiply the first one by 11 and multiply the bottom one by 7. Actually, I'm going to multiply the second one by negative 7. Okay, so that become negative 77 minus 56z, and then plus 42. And if I now add these 2 equations together, these 2 will cancel out. This actually come out to be just negative z, which is equal to negative 2. So now, therefore, z equal to 2. Now, notice that when I say z equal to 2, that is a plane. Remember, we talked about it back in chapter 1. Okay, when you have an equation can represent different things depending on what dimension it's in. So you can interpret z equal to 2 as in the variable z equal to number 2. But in our case, we are talking about a system of equation with 3 variables, and therefore everything happening in R3. Z equal to 2 is a plane in R3. As a matter of fact, it's the xy plane that moves up 2 units along the z-axis. Okay? Now with z equal to 2 established, I can now try to figure out what y is. So 7y plus 5 times 2 equal to negative 4. So that seems to be 10. So therefore tell me that 7y would equal to negative 14. So y equal to negative 2. Once again, y equal to negative 2 is also a plane. It's basically the xz plane. That's the plane that go out toward you and going up and move to the negative 2 spot on the y. And now I can find out what x is. So how do I find out what x is? Well, I'll just use one of the equation. X plus 4 times negative 2 plus 3 times 2 equal to 1. So look like that's negative 8. That's 6. So become negative 2. So it seems to me x equal to 3. So therefore, our solution in this case is 1 unique point. All right. So the general idea here is that we now find out that this system has an equivalent system that look like this. So therefore, in this case, what we did is, and that'll probably be the last thing I'm going to talk to you before we end today's video, is that we have this system, x plus 4y plus 3z equal to 1, 2x plus 5y plus 4z equal to 4, negative x plus 3y plus 2z equal to negative 5. And that turned into an equivalent system and that tell me what the intersection is. That become our answer. So essentially what we're doing is that we look at this plane. So let's see if I can do this. That might intercept in different spot and make them into 3 planes that go horizontal, vertical, and forward and back. Okay, front and back. All right. Unfortunately, that's all the time we got. So just give you a little idea as to what we're happening in 2.2. In 2.2, we're going to try to learn a method to solve the system of equation. We will still be doing what we call elimination, but we just do it differently. The reason why we do what we call matrix method instead of like do what we just did, because if you notice, when we are solving this system right here, a lot of things are changing. But if you think about it, the only thing that are actually changing are just the coefficient in front of the x, y, and z. We keep writing x, y, and z over and over and over and over and over and over again. But they actually doesn't do anything in the problem because they are just there. The actual things that are happening are the number in front of the x, y, and z. Like in this case, the y in front of y is 4, in front of y is 3, and now it becomes 7. That's the important part. The y is just there that I have to write out 3 times for no apparent reason. The z, we have a 3 and a 2, and then that becomes a 5. The z is just right there. It doesn't do anything. It's just keeping track of what it is. So the question is, can we develop a better way to keep track of things? And that's where matrix method come in. All right. So unfortunately, that's all the time I got for today's video. So I'll talk to you again soon. Bye-bye.